So thank you very much to the organizers for giving me this slot. I would like to talk very briefly, that's the last talk of the day, on a study that we have done of a nascent cluster that is bathed by an external, that seems to be bathed by an external UV field. And that's a quite common situation in extragalactic studies, so I think we can learn from this case. This is part of the PhD thesis of Esmeralda Drayet, and my collaborators are listed here. So we all know that clusters are formed within complex giant molecular clouds, and we know already from the talks on Monday that they are highly filamentary and highly substructured, and the densest parts of these clouds are called typically hub filament systems, or in this densest parts is where the fragmentation takes place more efficiently, and then as the cloud evolves, fragmentation proceeds and the cluster gets richer until we have the most massive stars that disrupt the cluster. So if we focus on one these particular fragments and we see how it evolves until reaching until becoming a stellar system, we start first with a pre-stellar core that Asunción Fuente nicely talked about this in the morning. And then that's a core that is gravitationally contracting, but it doesn't have any hydrostatic core in the center. Then the natural next step is the formation of the hydrostatic core. And then what we call the class 0 and first stages already contain the first stages of the disk formation, also of ejection of material through the poles. And in these stages, still the envelope mass is quite imperent. In subsequent stages, the envelope mass has already dispersed, either because of accretion or because of ejection, and we end up with a protoplanetary disk. So something very interesting that happens in this class 0 first stage is that in some cases, we can observe a very complex chemistry. And by this, we mean that we observe molecules with 6 or more atoms, and one of them is carbon. So this is very interesting because at some point it's going to set the conditions for planet formation. So we think, and I'll be very brief here, this sketch is inspired in the Herbst and Vendischok cartoon in the review. And we think that this chemistry, this very rich chemistry arises because as the dust grains move from the outskirts of the dense core of the pre-stellar core towards the center as the collapse proceeds, it progressively moves from cold parts of the core towards hotter parts. So at the beginning, there's the dust grain with a mantle with water-rich mantle, and because of the low temperature, the CO is frozen out onto the dust grains, and this naturally favors hydrogenation reactions, yielding HCO-rich molecules. But at some point, as these dust grains move towards hotter regions, the CO will be evaporated along with other molecules, and the mantles will be progressively more rich in very complex molecules that in the end they will also be evaporated. So that's when we are supposed to see this very complex chemistry. So that's an example of a spectrum with such a very complex chemistry. We almost have no continuum, so they are not easy to analyze. And according to this picture, we should see if we select the appropriate evolutionary stage, we should see in principle this phase, this complex chemistry why not in all the young stellar objects if we choose the proper stage. When this happens in high mass objects, we call them hot molecular cores, these chemically rich objects. And when this happens in the low mass case, we call them hot corinos. So that while for the hot molecular core, for the high mass case, we detect a lot of these complex chemistry objects, in the low mass case, this is not the case, at least until the 2020s. With the advent of ALMA and LERCH programs and so on, there's been a very important number of studies focusing, for example, one of the nearby clouds, such as Perseus or Orion, selecting or building samples of protostellar objects and these studies have focused on estimating the detection rate of hot corinos in these samples of protostellar objects. So, for example, the detection rates range from 20 to 60% more or less. But in these cases, all these targets are spread all over the cloud, so they can have distances from a few parsecs up to tens of parsec. So our approach here has been to select a cluster that is very compact and that the different local conditions of the cloud might not affect so strongly, or at least we can control them better. So for this, we focused on the Orion Molecular Cloud 1S cluster. It's to the southwest, about 0.1 parsec southwest of the trapezium, to the south of Orion BNKL, and about 0.2 parsec north west of the bar of Orion. So this is just the JWST view. And in this inset here, in the color scale, I'm just showing the 212 micron JWST image, showing the complexity already of this cluster, but also in black contours, I'm showing the ALMA data that we took at 1 millimeter, showing that a number of these infrared sources are still embedded in millimeter in dust emission. So they are very young. That's the view of the cluster with previous interferometers, previous to ALMA, that's the sub-millimeter array. And with ALMA, we get this view. So these data are a factor of 20 better sensitivity compared to the previous interferometric data. So because of this ALMA data that we have, of course, we can identify the molecular outflows in the region, which are a lot. And from this, we could determine that among these around 18 millimeter sources that we detect in the millimeter, 14 are already protostars, 14 are driving outflows. So these are our initial sample, let's say, of protostars where we want to look for complex chemistry. So in these previous interferometer observations with the sub-millimeter array, there were already two well-known hot corinos. So the detection rate with the previous interferometers were 14%. So our question now is, which is the detection rate with ALMA if we increase the sensitivity by a factor of 20? And the result is here. We obtain a spectrum for each continuum protostellar source. And we found that complex organic chemistry in 9 of them. This one is very marginal, but then is detected in the moment zero maps. So we could make the moment zero maps in an important number of transitions, not only these ones. And I'm showing here a summary of, as you can see, in the top panels, we have more simple molecules. In the bottom panels, we have more complex molecules. And in some of the simple molecules, we have like 13CS, H2S, and formaldehyde trace, like an arc-shaped structure facing with the tip facing or pointing towards the east, as you can see in these images. And also what we did is fit into the Gaussians in the moment zero of each one of these transitions, of the strongest transitions. And just we did a plot of the deconvolved size of each transition with the upper energy of the transition. And we can see a very big dispersion here, but we could say that for the highest energies, we have the smallest sizes. So that could be somehow consistent with internal heating, but we have a large spread here. So as a summary of this first part, we have, with the previous interferometers, we had 2 hot corinos among 14 protostars, which makes a detection rate of 14. And with our ALMA deep observations, we have 9 hot corinos, which make 64% of detection rate. So the first take-home message is, if we really want to study the chemical content of a region, we really need to go very deep. So the second part of the next step is fitting each one of these spectrum of each hot corino. And for this, we used an LTE model developed at IREP in Toulouse that is based on Python. It's within the CASIS scheme, and it simultaneously feeds numerous transitions of different molecules, including several physical components. And each physical component is defined by the parameters of the model, which are the source size, excitation temperature, column density of each species, line width, and velocity. So we have to give an input parameter file restricting the parameter ranges and giving initial guesses, and the code produces a synthetic spectrum, which in the end is minimized. So what we did is for each hot corino, we fit 4 different components. Initially, we grouped them by N-bearing, O-bearing, or S-bearing molecules, but soon we realized that we had to adjust these according to the sizes that we had measured for each transition. So in the first component, we included all the molecules that had, on average, smallest sizes, and in the in the fourth component, we included the most extended ones. So here, just showing this in a diagram, but there's no physics here. We just chose the components with according to the size of the transition. So the fourth component is the most extended one. So after fitting this model to all the cores, we had the parameters for each one of the 4 components. And for example, we could look at the excitation temperature that we inferred. And if we plot it against the component, we can see that the excitation temperature for the first component is higher, and it's getting colder progressively for the 2, 3, and 4 components. So that was expected because we chose the components to be larger in size. But it's interesting to see that we get the result that we were expecting. So far what we have done is for 8 hot corinos using the ALMA line cubes, fitting the LTE codes, also using the source size measured with the 0-order moments. And from this, we inferred the excitation temperature, line width, velocity, and the column density of each of the complex molecules. Then we can combine this with the ALMA continuum, infer the molecular hydrogen column density, and from this calculate the abundances of each of these species. Then we can, in parallel, work on the large scale information in the region to characterize the ambient cloud. As we have seen in previous talks today, in particular Pierre Palau talk, he showed that he applied the Vitrut code to the OMC1. So this data would be perfect to maybe combine with our data. But in particular here, we use the large scale dense gas of N2H+, kindly shared by Alvaro Acar. He published this in 2018, and he used ALMA combined with the 30-meter data of N2H+. So we are really tracing here the ambient cloud, the dense gas, but on large scales. And also we used in this work the large-scale ionized gas as inferred from VLT MUSE data. So this is work in progress, but I will show very quickly the results. So for the N2H+, we just calculated the moment 1, and we make a preliminary fit with Radex. And for the VLT data, we obtained the electron density maps from the ionized sulfur forbidden lines, and you can see here the electron density maps. The black square highlights the region we are studying, where our cluster is, but in the northeast we have the trapezium. So we can see that there's like a clear electron density gradient increasing towards the position of our cluster. If we zoom in here, we can see that this electron density follows like an arc shape, very well matching the millimeter continuum emission, but also this is now electron temperature from N2. And we can see that also the electron temperature matches very well the arc emission that we had seen previously in other lines. And here I'm just showing the DCN emission, and they match very well. So it seems that there's at least a morphological match. We need to make or study further whether there's really signs of real interaction, but at least morphologically, it seems that there's a very good match, suggesting that the ionization of the trapezium is really hitting at our cluster. So after gathering all this data, we built a correlogram to try to find potential correlations between the highlighted in orange, the hot Corino properties of column densities and abundances of the different molecules, and highlighted in blue, there's the ambient cloud properties. So just mentioning a couple of cases where we have seen interesting things. We recovered the well-known relation of dimethyl ether with ethyl cyanide. This had been seen before in previous works, in particular in Coletta 2020 work, who used the ALMA+IRAM30m telescope towards a sample of massive star-forming regions. And they found this correlation. We found exactly almost the same slope and essentially the same correlation that gives us confidence on our method here. Then we also explored previous correlations or ratios that have been proposed in the literature, in particular dimethyl ether to methyl formate, where some authors have proposed that this ratio is quite constant. But in our case, which are the magenta diamonds, we see that at least three of them are outliers, and they are actually sources which are facing or which are very close to the side of the cluster which is facing the trapezium. So could be affected by UV, but should be studied later in more detail. We also found potential correlations between S-bearing species and complex organic molecules, and also between ethanol and formic acid, which has been proposed previously. As for any potential relation with the ambient cloud properties, I must say that we didn't find any clear case. The only one is this one, which I'm really not sure at all, but might be interesting maybe to study in the future. It's a relation between the electron density NHC3N, which has been seen in previous works, but it's not really it's not an easy case. So we should look at it in detail. So just to summarize, to finish, the second take-home message is the environment could matter. We need to study this further, and Orion South is an excellent laboratory to do this. And together with the first take-home message that I gave, it's that sensitivity matters. And because we actually found an increase of a factor of 4 in the detection rate of hot corinos thanks to increasing the sensitivity. So I think I will stop here and thank you very much.
Thank you very much, Aina. Are there any questions? Everyone is tired. Are there questions on the Zoom? No? No.
So you're stating that you need to increase the sensitivity, but do you know, for instance, if you would integrate 10 times more, would you detect more 100% of hot corinos, or is there a lower limit on the intensity that can be emitted?
Yeah, that's a very good question. In our case, I think we're already reaching the limit, because in particular, or at least it could be that in our case, some of the millimeter protostellar sources that have not been detected in complex molecules are very close, lie in the side that faces the trapezium, so they could already be photon dissociated. So I think we're already reaching the limit, but we should keep observing even a little bit more deeper to be sure.
I wanted to ask you, you briefly shown the comparison of the molecular emission and what you see with MUSE. What do you make of the fact that you see DCN in such an environment?
I would like to study in more detail the case of DCN. I was surprised to find it to correlate so well with the electron density, and I should study a bit more. I'm not really sure right now if this was already expected or not. I should really check in the literature.